And when you combine the thingy with the other thingy, and you apply Einstein P equals Wendy square, you get nuclear detonation!
Hey, what did I tell you about doing Verzi Editz stuff?
I'm so sorry. I'm so
What did I tell you about leaving your corner of solitude?
I'm so sorry, you told me not to. I'm so sorry. Please forgive me, sir.
Get back to your corner and think about what you've done.
Yes, sir. I'm so sorry, sir.
Hi, welcome to Not Crash Course, where we totally don't have any intern slaves providing all of our intellectual content. How's it coming, Ryan?
I'm typing as fast as I can.
I expect something within the hour.
But you got it.
Today we're going to be covering the fantastic phenomenon that is nuclear chemistry. Bombs go boom. Alright, since I've been told not to focus on the historical development of scientific topics, Mr. Samsa, we're going to jump right into the science of nuclear chemistry. Alright, with our prior knowledge of atomic nuclei and protons and neutrons, we're going to refer to the collective form of protons and neutrons as nucleons and atoms as nuclides. Also, we're going to be using our prior knowledge of isotopes, which are atoms of the same element that have different number of neutrons, to further solidify the concept of nuclear chemistry. So without further ado, let's go! So one of the fundamental basics of chemistry is that atoms want to gain stability. Their never-ending goal is to gain or lose enough electrons to become stable. Well, believe it or not, the same goes for the nucleus. Just as the atom gains or loses electrons to stabilize its outer shell, the nucleus will gain or lose protons and neutrons to gain stability. This of course leads to transmutation, which is a change in the identity of a nucleus as a result of its changing its amount of protons and neutrons. Now a better question to ask is this: if the nucleus requires energy to displace all those protons and neutrons, well, what holds the nucleus together? That, my friends, is where nuclear binding energy is revealed. Yes, all you fans of complication. Nuclear binding energy is the energy released when a nucleus is formed from nucleons. It is the energy required to hold the nucleus together, and complementary to it, measures the stability of the nucleus. But I know you must be wondering, how do you calculate nuclear binding energy? Yes, all you clever minds sitting out there in the audience. I wish there was a simplistic way to answer that, but unfortunately, I'd be lying to you. There is obviously only a complicated process that takes the form of the mass energy equivalence formula. For all you nerds out there, that could be translated to E equals mc squared. Yeah, who'd guess we used the most famous equation in scientific history to explain nuclear chemistry? I didn't, but that's besides the point. Before we can use E equals mc squared to calculate nuclear binding energy, we actually have to backtrack and calculate mass defect. Mass defect is the difference between the total mass of the individual nucleons in a nucleus and the nucleus as a whole. I'm sure a lot of you are confused by that, so we're actually going to use an example. Take the nucleus of an atom of helium. A helium-4 nucleus has an AMU of 4.0026, but when you carefully calculate the sum of the two protons, neutrons, and electrons that make it up, you're surprised to see a cumulative total of 4.032 AMU. So there's a difference between the AMU of the combined nucleons and the nucleus as a whole. That right there is mass defect. Sticking with our helium example, we first have to convert our mass defect into energy units, which may or may not involve a simple conversion problem. You multiply our mass defect of 0.030 by the atomic mass unit of 1.6605 times 10 to the negative 27th kilograms to get a grand total of 5.0441 times 10 to the negative 29th kilograms. And now we can implement this into the m portion of E equals mc squared, and we can easily substitute c for Einstein's constant of the speed of light, which is 3.00 times 10 to the 8th meters per second. Now we just simply multiply the two together to solve for energy in E equals mc squared, and we are left with a grand total of 4.54 times 10 to the negative 12th joules of energy. Not complicated at all, am I right? Yeah, who am I kidding? We're all confused at this point. Well, I guess we can talk about two topics that are relatively comprehensible, which is nuclear fusion and fission. So these two terms are antithesis to each other. Nuclear fission involves a large nucleus separating into two nuclei, and nuclear fusion involves two smaller nuclei coming together to form a large nucleus. See, that's pretty understandable, right? Taking a look at a chart showing the relationship between binding energy per nucleon and mass number, elements with high binding energies are relatively stable, others not so much. By taking mass number into consideration, elements with lower mass numbers tend to merge their nuclei together, forming a bigger nucleus, whereas elements with large mass numbers separate their nucleus into smaller nuclei. To put it simply, lower mass numbers equals fusion and higher mass numbers equals fission. Ho ho ho! We are not done yet, my perpetually confused cohorts. We have barely scratched the surface on nuclear chemistry. There's still alpha, beta, and gamma decay. So we all know the presence of radioactivity, which leads to radioactive decay. What are the types of radioactive decay? Well, I just listed them a couple seconds back. Starting off with alpha decay, it is the result of the formation of an alpha particle. They are formed when 2 protons and 2 neutrons bind together. Alpha decay is typically limited to very heavy nuclei. The most notable example of alpha decay comes from uranium-238, for when it goes through alpha decay, it becomes thorium-234. Beta decay is different in that it doesn't involve the proton or neutron whatsoever. It's all about the electron. Beta decay involves the emission of a beta particle, which is an electron emitted from the nucleus. There's a lot of emission when it comes to radioactive decay, but our third example is actually intriguingly different. Gamma decay is emitted in the form of gamma rays, which are high-energy electromagnetic waves released from a nucleus as it changes from a ground state to an excited state. Gamma rays are a form of electromagnetic radiation but have a much shorter wavelength and are very higher in energy than visible light. Recall in this case Bruce Banner, you know, the guy that because of an accident now has extreme anger management issues? Let's take a quick peek at what Tony Stark had to say to Banner regarding his accident.
Hey, I read all about your accident. That much gamma exposure should have killed you.
That's because it would! If gamma rays penetrate our skin, which they easily can, they would destroy our cells and we would become a pile of nothingness. We would become nothing. Oh my gosh, my head hurts. These scripts are getting too complicated. Alright guys, thank you so much for joining us on this episode of Not Crash Course. Hey Ryan, did you finish the script?
Yes, sir, right here, sir.
Ryan, this is a flashlight.
I know. You're covering light energy for your next video.
Oh, okay. Shoot, get out of here.
Okay, sorry, sir.
Alright guys, if you enjoyed this episode, please subscribe to Verzi Editz for more videos exactly like these, and hopefully you know a little bit more about nuclear chemistry than you did before you watched the video. Until then, I'm Dom, and Ryan, you want to say something before we leave?
Don't drink all the cups.
He's a special little snowflake.
Mm-hmm.
Why would he hand me a flashlight?